Sound is a wave. It is a longitudinal mechanical wave. So, all that we have learned about the properties of mechanical waves applies here. The linear wave equation, the sinusoidal shape of the perturbation of the medium, speed equal to wavelength times frequency. Sound is a perturbation of a medium. For example, air. Molecules vibrate back and forth, backward, forward, and about an equilibrium position. These vibrations, they propagate and transmit energy and also information. The velocity of propagation of sound depends on the mechanical properties of the medium of the fluid or the solid. That is, on how fast it is recovering from the perturbation. If you remember from when we studied elasticity of objects, we introduced the bulk modulus and the Young modulus. These parameters characterize the flexibility of a medium, and they have a clear effect on the velocity of propagation of sound in that medium. In a fluid, the speed of sound is given by the square root of the bulk modulus over the density. In a solid, the speed of sound is given by the square root of the Young modulus over the density. In the spherical case, for an ideal gas, we can write the velocity as the square root of gamma RT over m. Well, here gamma is the adiabatic index that depends on the kind of gas and its molecular structure. R is the gas constant, which is 8.31 joules per mole per Kelvin, and T is the absolute temperature, the temperature in degrees Kelvin. Remember that 0 degrees Kelvin corresponds to minus 273.15 degrees Celsius. M is the molecular mass. This equation tells us that the speed of sound in a gas depends on the gas and on the temperature. The higher the temperature, the higher the speed. For air at sea level, we can write V equal to 331 times the square root of T over 273. Knowing this, we can build a sonar, which is a device that determines the position of objects based on the echo, the time that sound takes to reach the obstacle, be reflected off of that object, and get back to the source, which is what bats use to move in the dark.
This is an audio
No,
set.
not that guy.
He talks
Well,
with
maybe with his bat stuff.
and a high-frequency generator receiver.
You took my sonar concept and applied it
Under
to everything.
this expression, we see that the speed of sound does not depend on the frequency, which is good. Otherwise, you will be sitting in a far row in the theater and you would hear different instruments from the orchestra at different times, and that is not what actually happens. Unless instruments are too far apart, of course. Knowing the speed of sound in air can help us determine the distance from an electric storm. When there is a lightning, we see it first, and after some seconds, we hear it. The lightning creates an expansive wave, a sharp increase in temperature that makes the air glow and produces an explosion. Because light travels much faster than sound, we first see the flash of the lightning almost instantaneously. And because sound travels slower, it takes more time for it to reach us. So if we count the seconds since the lightning until we hear the thunder, well, just think that if light takes about 330 meters per second, then every 3 seconds is 1 kilometer. May science be with you.